Hi everyone, my name is Adam Kirkovich, and the purpose of this video is to showcase DMBDI Explorer, which is an interactive tool that allows for data access, analysis, and visualization of the DMBDI dataset. Before we go any further into this, just a few words about DMBDI. So it stands for Dystrophy Myotonica Biomarker Discovery Initiative, and it's been a collection of researchers worldwide, including clinicians, geneticists, and bioinformaticians, who gathered together with the purpose of generating and analyzing a large microarray data set looking at myotonic dystrophy type 1. So we've had more than 30 participants, study participants, including both DM1 positives and healthy controls. There are multiple things that can be done with the data set. So, for example, at the University of Glasgow, we've measured an effectiveness of a potential DM1 treatment in a simulated clinical trial, but we expect that other uses of the dataset will be coming out following the public release of the tool. Okay, I'm going to share my screen just now, and I'm going to show you the tool. So the tool has been implemented as a website, which means you can use it anywhere as long as you've got a web browser. You just need to type adam.kirkovich.com and your omnibus. And the website's been password protected because it allows for execution of arbitrary Python code. But I'm happy to share the code. I'm happy to share the password with any bona fide researcher. Right, after you've opened the tool, you can click on this template here, but please don't modify it. Create a copy which will contain something specific, something unique to yourself, such as your name or maybe your affiliation. Okay. So as you can see, the tool is interactive, so we can execute any code that we want by pressing Shift-Enter. Potentially the most interesting thing is that we can analyze any gene that we're interested in. So the platform, the microarray platform, obviously targets whole genome. So all of the data is in here. But I think the most interesting property of the tool is actually producing those plots, which I'd like to call railway plots. The way we've come up with those plots is we've looked at what genomics community has been doing with Manhattan plots, and we applied this to transcriptomic studies. So the way the plot works is that on the x-axis, we have the genomic coordinates looking at the locus of interest, and in this case, it's the locus containing the gene TNNI1, which is troponin 1 slow skeletal type, and that's situated on chromosome 1. On the y-axis, we have logged p-values of statistical tests which check for splice in, splice out events versus the null hypothesis of neutral gene expression. And if you look at any of those groups of single colored dots in here, these are probe sets which target specific sites of this gene, usually exons or UTRs. We can use the data that we've generated to study myotonic dystrophy, but we need some extra information about DM1 status, some sort of measurement. So the binary information about the status, such as affected versus unaffected, certainly works and has been used before. But a better way to do this would be to have something a bit more detailed. And in our case, what we've used is we've used the mode of the length of DM1 repeat assayed from participants' blood. And that's been done in Professor Darren Monkton's lab at the University of Glasgow. Let's look in a bit more detail at probe set 2450829 and how this blue group of dots was generated. So as you can see, there are four linear regressions, and that corresponds to the 4 probes which belong to the probe set. And each linear regression indicates strongly downwards trend of expression at this site, at this probe set, with measured allele length from the DM1 repeat from blood. And to each of those linear regressions, we can associate a p-value of the statistical tests versus the null hypothesis that there is in fact no trend. So the thing about those p-values is that on their own they will be quite hard to visualize. So what we do instead is we compute a logarithm of the p-value, and after we've logged it, because p-values are defined on the interval from 0 to 1, what we obtain is a negative value. Negative values are actually quite difficult to reason about, so we multiply it by -1, and the next thing that we can do is we can actually multiply it by the direction of the slope to see if this was a splice in or a splice out event. I'll just demonstrate it quickly. So we have to remember that it's a decimal logarithm. And as you can see, this p-value here of this first linear regression, that's going to make its way into the plot as -4.15. So that's going to be somewhere here. When we look at this plot, another thing that comes to mind is, what are those red lines? So we can see that there is this faded red line and this saturated red line. So I'm going to talk about the faded red lines first. So the faded red lines, they capture the traditionally used level of statistical significance, p-value of 0.05. And their meaning is that if we were to study 100 probes, under the null hypothesis, we would expect about 5% of those, so about 5 of the probes, to come either at the top of the faded line or at the bottom. The meaning of the saturated lines is slightly more interesting. So these lines were produced by computing the Bonferroni correction of this statistical threshold, and their meaning is that if we were to look at 100 genes like TNNI1, we would see in about 5 genes probes which would go outside of the saturated red lines under the null hypothesis. Let's dig a bit deeper into the biological significance of this data. The first thing we can look at is this paper due to Batra and collaborators, which came from Professor Charles Thornton's group at Rochester. And although they've used a different muscle data set, they have identified the same probe set in TNNI1 that comes up highest in our analysis. And we can verify that by looking at table S5 in the supplementary material. So that's the table here. And I've already downloaded it. And as you can see, it lists all the probes with potential alternative polyadenylation events, and TNNI1 is one of those listed here. And what it shows is, it shows that this probe set was downregulated, was spliced out, just like in our data set, because the fold change is less than 1. And it's also coming up as very highly significant. We can get to know a bit more about this gene by looking at ensemble. The first thing that really shows when we look at this collection of transcripts is the fact that there appear to be alternative 3' UTRs in this gene, and these are potential sites of alternative polyadenylation. So we have to look at this from right to left because the gene is on the reverse strand. The specific probe set of interests, 2450829, that appears to be targeting a 3' UTR, which is unique to just a single transcript. And this allows us to make some potential guesses that this particular transcript, the levels of this particular transcript, could be a good indicator of myotonic dystrophy, a good biomarker of myotonic dystrophy. The tool is not limited to just looking at a single gene, so we can look, for example, at other genes of interest, also in muscle. So one example would be MBNL1, where there appear to be two probe sets, which are potentially interesting, but we get somewhat conflicting readouts within a probe set. Or we could look at, for example, MBNL2, which I've chosen because it appears to, instead of giving a spliced out type of signal, it appears to be giving spliced in type of signal. So that's quite interesting. Other things that we can do with the data set is, because measurements of mirrors have been also taken, we can access that and use that in our linear regressions. So we could do muscle metal and mirrors, and that gives us the mirror scores for all the participants. Another thing we could be trying to do is to discover blood biomarkers. So we obviously have metadata for blood, and we've got entire blood data sets. So for example, we could look at TNNI1 in blood. Like this, for example. And obviously, sorry, model LU, there we go. So that doesn't give us as much signal. The primary reason being that TNNI1 is not really expressed in blood. Okay, that's everything I've got to say for now, and thank you for listening.